In this video, I am going to explain some of the important theorems from the first unit of advanced algebra. So here, let's begin with the first lemma, that is, prove that homomorphism of V and W is a vector space over F under suitable operation. So here what we have to do, we are going to prove that homomorphism of V comma W is a vector space over the field F under suitable addition. It means here you are going to use an operation addition. Okay, so here to prove homomorphism of V comma W is a vector space over the field F. So here to prove this, what we have to do is, first you have to say that S plus T and S plus T, okay, S plus T, so here S plus T and alpha S belongs to this homomorphism of V comma W. What are they? S plus T, okay, yes, capital S plus T, capital S and capital T, S plus T and alpha S are the elements of homomorphism of V comma W. So after that, what you will do is, using these two, you will prove all the conditions to say a non-empty set as a vector space. Okay, let's start from the first step. So here first what you are doing is, you are taking two elements from homomorphism of V comma W, that is S and T. Okay, after that you are defining something, that V of S plus T. Okay, V of S plus T is equal to Vs plus Vt. So here S and T all are in capital letters because you are taking these elements from homomorphism of V comma W, that is this and S and T are the functions. Okay, because you are choosing this element from homomorphism of V comma W. Okay, so here you are define V of S plus T is equal to Vs plus Vt. So here this V belongs to the vector space capital V. Okay, now what you are going to do is, you are going to prove S plus T is an element of homomorphism of V comma W. So here you are defining this. The reason you are defining this is, using this you will prove S plus T is an element of homomorphism of V comma W and alpha S is the element of homomorphism of V comma W. Okay, so here first we are going to prove S plus T is an element of homomorphism of V comma W. So you are taking two elements from the vector space V. The reason for taking these two elements from the vector space V is, you will use these two elements in the homomorphism conditions. That is, if you want to say S plus T is an element of homomorphism of V comma W, you have to prove two conditions. If these two conditions are satisfied, then you can say this S plus T is an element of homomorphism of V comma W. So let's start. This is the first condition, and after proving this condition, you have to prove this. Okay, so to prove V1 plus V2 of S plus T is equal to V1 of S plus T plus V2 of S plus T. These are the conditions for homomorphism. These two conditions we will learn in the definition of homomorphism. Okay, in the vector space. Okay, so let's proceed. So you have to prove this. Okay, to prove this, what we are doing is, consider the left hand side. V1 plus V2 of S plus T is equal to, you are going to write this in this format. Can you see that? Okay, you are going to write this in this format. So that is how you are writing V1 plus, I am not going to give you elaborate explanation about substituting the values here, because if you observe it very clearly, you can understand it by your own. Okay, so I don't want to waste time on all those stuffs. Okay, so when you use this here, you will get V1 plus V2 of S plus V1 plus V2 of T. So after that you are multiplying V1S plus V2S, then put this plus and v1t plus v2t. After that you are writing v1 terms in as one group and v2 terms in another group, so that you will get this. After that you are taking v1 from this, v1 common from this, and b2 common from this, so you will get this. So finally you have proved with the help by taking left hand, considering left hand side, you proved the right hand side. So first condition of homomorphism is satisfied, and the second condition is to prove alpha v of s plus t is equal to alpha of v of s plus t, where alpha belongs to the field f. Already we know that we take the scalars like alpha, beta all from the field f, right? So here also you have to prove this alpha v of s plus t is equal to alpha in the outside, then v of s plus t. This is what we have to prove. So for that you are considering the left hand side. So here you have considered, and you are writing this with the help of this. Okay, you are writing in this format. Okay. So you get alpha v of s plus alpha v of t. Now we are taking alpha. Now in this step, what you are doing is you are writing v and vs in one group. You are writing alpha outside. Okay, alpha of vs plus then alpha of vt. Similarly, you are doing this too. Now from this two terms, what you are doing is you are taking alpha common, so that you get alpha of vs plus vt. So finally, from the inside this bracket, what you are doing is you are taking v common, so that you get alpha of v of s plus t. So finally you have proved the two conditions of homomorphism. So from this you can say that the element s plus t is an element of homomorphism of v comma w. So now before proving alpha s belongs to homomorphism of v comma w, what you are doing is here you are proving homomorphism of v comma w is an abelian group. That should also we have to prove. Okay, so you are proving that. You can also do like this, that is, you proved this, right? S plus t is an element of homomorphism of v comma w. Now immediately after proving this, you can prove this also. You can write this part also, nothing wrong in that. Okay. So here I am going to, here what we are doing is we have in this part, what you are doing is you are going to say this homomorphism of v comma w is an abelian group. Okay, so let s comma t belongs to homomorphism. You are taking two elements from homomorphism of v comma w. To say this this homomorphism of v comma w is an abelian group, we have to prove the condition this. That is, we know that abelian group means it should satisfy the commutative property. Then that group is called what? Abelian group, right? That is, there are a lot of conditions like closure property, associative property, identity property, right? Inverse property. These conditions set, if satisfied all these conditions, then you can say it as group. With all these conditions, if that set also satisfy commutative property, then you can say that group as an abelian group, right? So here finally, if you want to say this homomorphism of v comma w is an abelian group, what you have to do, you are here going to prove that with the operation addition. Okay, with the operation here you have to prove s plus t is equal to t plus s. If you prove this, then you can say that homomorphism of v comma w is an abelian group. So here consider v of s plus t is equal to, this can be written as vs plus vt. How you have wrote this? You are writing this with the help of this. So from this you can say what you are writing is, you are writing this term first and then you are writing this. Just interchanging the place of the terms. That's what happening in this step. Now taking v common, v of t plus s. So from this you can you are writing the left hand side and right hand side. So from this you can cancel this v, because v is in both the sides, right? So you can cancel v, so that you get s plus t is equal to t plus s. So commutative property satisfied. So we can say under addition, homomorphism of v comma w is an abelian group. Okay, after that what we are doing is, now you are going to prove alpha s belongs to homomorphism of v comma w. Okay, this element belongs to homomorphism of v comma w. The reason behind finding all these things is because to prove homomorphism of v comma w is a vector space, there are some conditions should be satisfied, right? In that condition you are going to use s plus t and alpha s, all these things. So before applying all these values you have to say, right, these two elements belongs to homomorphism of v comma w. That is why you are doing all these things before saying homomorphism of v comma w is a vector space over the field f. So here next to prove alpha s belongs to homomorphism of v comma w. So for we know that any scalars you are choosing that will be from the field f, that the scalars will be in the field f, right? So here alpha belongs to f and s belongs to homomorphism of v comma w. Now we again you are defining something, v of alpha is equal to alpha vs. Again you are defining, okay? You should not forget this. If you forget this step you could not proceed the proof. Now we are taking two elements from the vector space V. v1 comma v2 belongs to capital V. So we know that if you are here proving that two conditions for homomorphism, if you prove these two conditions then you can say this alpha s belongs to homomorphism of v comma w. So here to prove v1 plus v2 of alpha s, you have to say this element belongs to homomorphism of v comma w, right? So that is why v1 plus v2 into alpha s is equal to v1 of alpha s plus v2 of alpha s. This is what we are going to prove. So to prove this, what you are doing is you are considering the left hand side first. v1 plus v2 of alpha s is equal to, you are writing this in this format. If it is like this then you can write like this. Similarly if it is like this, you are writing this in this format. Okay, alpha of this alpha into, here what we have in the place, here we have v, in the place of v here we have v1 plus v2. So you are writing v1 plus v2 into here in the place of s, here also we have s, so we are putting s. So from this what you are doing is put alpha into multiplying, so we get v1s plus v2s. So from this you are, after that you are multiplying alpha with the terms they are inside the bracket, right? So we get alpha of v1s plus alpha of v2s. Right, from this what you are doing is you are taking v1 outside, you are writing alpha inside the bracket, so that you can do that. Okay, v1 of alpha is equal to v2 of alpha is, right. Next you are going to prove the second condition of the homomorphism, that is to prove if alpha belongs to f, you have to say lambda v of alpha is equal to lambda of v of alpha s. Because the homomorphism definition you use what you will say, alpha v of that required element. Okay, the element that you are going to say homomorphism of, you will write in this format, right? But here in the place of alpha you are putting lambda. Why? Because already we have to prove alpha s belongs to homomorphism of v comma w, right? So here already you have alpha. If you put alpha here again then you will get confusions. So that is why instead of alpha here you are using another one scalar, that is lambda v of alpha s is equal to lambda of v of alpha s. Okay, so now consider the left hand side, and from the left hand side what you are doing is you are writing this from this format. You are right, with the help of this you are writing this. Okay, you are writing this by the way you are defining. Okay, now you get alpha of lambda v of s. Now alpha of lambda v and s in one group. Now bring that lambda outside and alpha in. So lambda of alpha of vs. So you get lambda of v of alpha s. Okay, now from this you finally you brought the right hand side of this condition, so that you can say this the two conditions of the homomorphism was satisfied, so that we can say alpha is belongs to homomorphism of v comma w. Now you have to say that homomorphism of v comma w is a vector space over the field f. To say a non-empty set as a vector space over the field f, it should satisfy some of the conditions. That is, it should satisfy 4 conditions. So let me explain you what are they. That is, what you are doing is, let S comma T belongs to homomorphism of V comma W and V belongs to capital V. To prove V alpha of S plus T is equal to V of alpha S plus alpha T. This is the first condition of to say a non-empty set as a vector space. So you have to prove this first. Okay, so to prove that, what you are doing is, you are considering the left hand side. V alpha of S plus T is equal to this alpha outside, then V of S plus T. You are writing this in this format. Okay, so after that, alpha of multiplying this, you get Vs plus Vt. Okay, then multiply alpha in, so that you get alpha of Vs plus alpha of Vt. Now you bring V outside, so that you get V of alpha S plus V of alpha T. Now from left hand side and right hand side, you can cancel that V, so that you finally we will get this. So the first condition of the vector space is satisfied. Now let us move on to the second condition, to say a non-empty set as a vector space. That is the second condition is V of alpha plus beta into S is equal to V of alpha S plus V of beta S. This is the second condition. Okay, V of alpha, you have to memorize this. V of alpha plus beta into S is equal to V of alpha S plus V of beta S. So to prove this, what you are doing is, you are considering the left hand side first. Now this can be written as alpha plus beta into Vs. Okay, by our definition. What definition? This definition. This is how you are defining, right? So from this, you are writing like this. Now what you are doing is, alpha of Vs plus beta of Vs. So here what you are doing is, you are bringing this V outside, right? So you get V of alpha S plus V of beta S. So from left hand side and right hand side, you will cancel this V, right? You can cancel this V, you can take this V common. That is, the left hand side is V of alpha plus beta into S is equal to, in the right hand side you have this, here also you have V and here also you have V. Take V common, so that I can write what? Alpha S plus beta S, right? So V and V get cancelled, so that you have proved the second condition of the vector space also. Now we are passing on to prove the third condition, that is V alpha of beta is equal to V of alpha beta into S. This is what the third condition to say a non-empty set as a vector space. That is V alpha of beta is equal to V of alpha beta into S. Memorize this. Okay, memorize these conditions. Consider left hand side, then is equal to alpha of V of beta S. Okay, how you are writing this? This plays a key role, right? Okay, now alpha of beta, bring this beta outside and V in, so that you get now alpha beta in one bracket and Vs in another bracket, so that you get now bring this V outside, so that alpha beta into S you get, so that the third condition of the vector space is also satisfied. Now here is the last condition, that is to prove V of 1 minus 1 into S equal to Vs. This is what the last condition that you have to prove. So that here you have 1, right? You are talking about 1 here. What is that 1 here? So you are telling that let 1 be the unit element in the field F. Okay. Now consider the left hand side. We have 1 into s equal to 1 into vs. So from this you get 1 into s, that is in the left hand side you have v of 1 into s, and in the right side hand side you have vs. So v and v get cancelled, you get 1 into s equal to s. So from this the fourth condition of the vector space is also satisfied. So finally all the four conditions to say a non-empty set as a vector space have been satisfied. So that what you are doing is, in the finally you are saying homomorphism of v comma w is a vector space over the field f. So hence the proof.